Hello students, how are you? I hope you are all doing well. So today we will study the magnetic dipole moment of a revolving electron. Okay. Uh, you might have heard about the Bohr model in quantum mechanics, or we can say in modern physics. So this topic is related to that. So as per the Bohr model, we know that the electrons revolve around the uh, like the electrons revolve around a certain nucleus. Okay, so here in this derivation we are going to assume that there is a nucleus that is situated at a constant place, and its charge is plus Ze, and one electron with charge minus E is revolving around it, and the direction of motion of the charge part, the electron is it's anti-clockwise. Okay, so if the charge particle if the direction of motion of the electron is anti-clockwise, then obviously we know that if it is moving with constant speed, then it will produce a current, and the direction of that current will be nothing but it will be clockwise, because the direction of current is always opposite to the direction of electrons. So here it will be clockwise. So there will be a clockwise current due to the motion of the electron. Here the electron, I'm repeating again that here the electron is revolving with uniform speed. Okay, and that uniform speed is let me write, revolving with uniform speed, and that speed is v. The uniform speed is v. If the uniform speed is v, then the flow of electron will produce the current. And now one thing, if it is producing the current, then what will be the equation of that current? Okay, so we know that the current will be I equals to, we know that charge upon total time, total charge upon total time, total taken time to revolve the electron. Okay, so here the particle is revolving in the uniform circular motion, so that's why the charge on the particle is nothing but it is E. Okay, the magnitude of the charge we are taking here, and T is the total time taken for one revolution. Okay, or we can say one round around the circle. So here, if the speed is v, then if speed is v, then T will be nothing but it will be the circumference divided by its speed. Okay, because the time period is nothing but the total distance and divided by its speed. So it is 2 pi r upon v. Now we will put this in the equation of current. Then we will get I equals to E upon 2 pi r upon v. Now if this v will go to the numerator side, so it will be I equals to EV upon 2 pi r. So this is the equation of current which is flowing in the this orbit. Okay, or we can say flowing in the orbit, or we can say the current produced due to the flow of electron. Actually this will be the correct term. Now current we have find out. Now the one thing that we are going to find out is magnetic moment. Okay, so magnetic moment is, here we are going to take, we are going to take here the magnitude. Okay, actually the magnetic moment is nothing but, now let me write, the magnetic moment, it is nothing but mu L equals to I into A vector. Okay, here mu L is the magnetic moment vector, and I is the current, and A vector is the area vector of the area of the, we can say, circle. Here for this case, area of the circle. So now we are going to take the magnitude here. So its magnitude its magnitude will be mu L equals to I into A. Okay, because here I is the already in the magnitude form and A is nothing but magnitude of area vector that we have used here. Now, if it is in the magnitude form, then now we know that the area of the circle is nothing but pi r square. So mu L will be I into pi r square. Okay, because we know that here A is nothing but pi r square for a circle. And now we will substitute the expression for current. But have you seen that why I'm writing here L? Because here the magnetic moment is nothing but due to the orbital motion. Okay, so that's why it is sometimes called as orbital angular momentum also. Sorry, angular magnetic moment. So that's why here L is written. Now that we are going to see that why it is because of the orbital momentum, because the term L is going to appear in the equation. So now substitute I equals to EV upon 2 pi r. So if we substitute I, because from the above equation, we have written this I equals to EV upon 2 pi r. Now, if we substitute it in the equation, then what we will get? Our equation will become as mu L equals to in place of I EV upon 2 pi r, and here it is multiplied with pi r square. So pi and pi will be cancelled out, and this one r will also be cancelled out by r, means the square is cancelled out by r, and there will be one r only. So it will become mu L equals to EVR upon 2. So this is the equation EVR upon 2. Now we are interested in to convert this into the angular momentum. So how can we convert? If we multiply the mass of electron in the numerator and denominator both, then what we'll see? So let me write here. Multiply the mass of electron Me to the numerator and denominator. So what we will get? Here we will get mu L equals to E into MEVR. Here Me is the mass of the electron, okay? Don't get confused. Me. Okay. So now as we can see here that MVR is nothing but we know that it is angular momentum. So mu L is E upon 2m into L. A into two E into sorry, mu L equals to E upon 2m up into E. So this will be the equation for magnitude of orbital angular moment. Sorry. So it will be the equation of, it is nothing but it is the magnitude of the magnetic magnetic moment. It is the magnitude. It is the magnitude of magnetic moment. Now, in the vectorial form, we can write in vector form. In vector form, we can write mu L vector equals to minus of E upon 2 me L vector. And I'll tell you why there is a negative sign. Because here, what we have taken here, the we can say the exact charge of electron. Charge of electron is it is minus E. So that's why we have taken here minus E, and then the actual vector form will vector form of the magnetic moment will be mu L vector equals to minus E upon 2 me into L vector. So what does it show? It is basically showing that the direction of magnetic moment and the angular momentum is anti-parallel. They are anti-parallel to each other. Fine. And we know that the direction of angular moment is nothing but it is the direction of, if we see from here, the direction of magnetic moment is it is mu L vector equals to I a vector, where the direction of the mu L vector will come from the direction of area. Okay, it will come from the direction of area, and the direction of area will be as per the right hand rule, because as per the right hand rule here in the if you see the circular motion here, so the electron is revolving in the anti-clockwise direction, so current will be flowing in the clockwise direction. So if the current is flowing in the clockwise direction, then as per the right hand rule, we should revolve our fingers in the clockwise direction, so we can see that the direction of area vector will be into the page. Okay, into the page. So that's why we have drawn also here the symbol cross symbol, that is representing that the direction of area is also into the page, and because of that the direction of magnetic moment will be also into the page. So if the direction of magnetic moment is into the page, then we can say that the direction of angular momentum is out of the page. So that's how we can determine their directions also. Okay. Now let's say that we should take some case that if in place of electron, if there is a positive charge particle, then the magnitude of the angular momentum and the magnitude of orbital moment or sorry magnitude of or orbital orbital momentum, it will be mu L divided by L will be nothing but it will be E upon 2 me. This is the famous relation, and sometimes it is asked in the exams also, that what is the ratio of magnetic moment and angular momentum, and it is nothing but it is the charge upon twice of the mass. And the value of E upon 2 me, it is experimentally proved also that it is value is nothing but it is 8.8 into 10 to the power 10 coulomb. Let me write. And it is called as gyromagnetic force. It is called as gyromagnetic ratio. Gyromagnetic ratio. One second. Sometimes like not write, they will not write that the ratio of magnetic moment and the angular momentum. They will write gyromagnetic ratio. So it will be the same thing, gyromagnetic ratio. And E upon the value of E upon 2 me will be nothing but it will be 1.6 into 10 to the power minus 19 divided by 2 into 9.1 into 10 to the power minus 31. It will be approximately 8.8 into 10 to the power 10 coulomb per kilogram. This will be the value of gyromagnetic ratio here, 8.8 into 10 to the power 10 coulomb per kilogram. Now, if we talk about Bohr's second postulate, what is the Bohr's second postulate? According to that, angular momentum is nothing but it is quantized. And how it is quantized? Let me write. Bohr's postulate, what it is? L should be n times h cut, where h cut is nothing but reduced Planck constant, or we can write here L equals to n h upon 2 pi, because we know that the value of h cut is h upon 2 pi. So if we place this value, in the above equation, then we will get, let me write, because in the magnitude form we know that it is EL mu L equals to E upon 2me into L. And if we replace the value, then we will get mu L equals to E upon 2me and multiplied by nh upon 2 pi. Okay, this will be the exact value of angular momentum. Sorry, angular moment, magnetic it will be the value of magnetic moment. So if it is the value of magnetic moment, then what is its minimum value? So for minimum value, for minimum value of the magnetic moment, we can take n equals to 1. Okay, or we can say in terms of Bohr's model, n equals to 1 means first orbital. So it will be, we should write here minimum magnetic moment equals to eh upon 4 pi, 2 into 2, 4 pi me. It will be 4 pi me. Okay, and its value will be if we calculate, it will be 1.6 into 10 to the power minus 19 into 6.626 into 10 to the power minus 34 divided by 4 into the value of pi is 3.14 and me is nothing but 9.1 into 10 to the power minus 31. And what is the SI unit of magnetic moment? It is ampere meter square. So it will be ampere meter square, because basically it is current into area only. So that's why it will be ampere meter square. So its value is, if we find out, calculate 9.27 into 10 to the power minus 24 ampere meter square. And this value is called as Bohr magneton. Okay, so we should write here mu L minimum equals to 9.27 into 10 to the power minus 24 ampere meter square, and this is called as Bohr magneton. This is named as it is called as Bohr magneton. Okay, so this is all about the magnetic dipole moment of a revolving electron. And here we started with that one electron was revolving around a nucleus of plus charge at E. And because of that, there was a current flowing in the opposite direction of that motion of the electron, that is in the clockwise direction. And the current was nothing but it is the charge of electron divided by the total time taken in the one revolution. So it was A upon T. And now the time period can be found out. It can be found by the total distance by speed. So it will be 2 pi r upon V, and then I equals to E upon that rest is we can say all the it is all the derivation. And if you have any doubt in this derivation or whatever you like to ask in the question, then you can put up in the comment section, or you can then we will try to solve it in the next video or in the comment section itself. Okay, thank you.